So here we have a uniform disk of mass m. A string is wound around it. Now the string's mass is negligible, so we can pretend the mass of the string is 0. We're going to look at the forces acting on this disk as it falls vertically downwards. We will get the acceleration of this disk, and we will show that the acceleration of such a disk, such a uniform disk, is related to the acceleration of a uniform disk rolling down an incline. So we'll see a very simple connection. If we know the acceleration of this disk here, we can very quickly get the acceleration of this disk falling vertically. Okay, so the center of mass is at the center of rotation. The mass is m, the weight is mg. Obviously this is not the only force acting on the disk. The string is pulling on the disk because the disk is pressing on the string. The string is wound around here, of course. While this part of the string is in contact with the disk, the force on this bit of string due to the string here is equivalent to the force on the disk. While the string is in contact with the disk, we can imagine that this bit of string is part of the disk system. After all, the string has mass 0, so all the mass is included here. M is just the mass of the uniform disk. Okay, so we have a force acting on this piece of the string, which we can think of as a force on the disk. So that force is constant, vertically up, of course, along the string. We'll call that force T. It's constant because the weight of the disk is constant. So the picture of the disk in this position is identical to the situation when the disk is, say, further down here. We still have the same force acting down, so there's no reason why the tension T pulling up should change, and indeed it doesn't. Everything looks the same because the string's mass is 0, so unwinding the string doesn't change anything. Now, since the disk is obviously rotating about the point C, we can apply the principle of angular momentum. So let's consider the sum of the external torques on the disk about the point C. Well, the weight has no external torque about the point C because the distance of the point C to the line of action of the weight is 0. Point C is on the line of action. T has an external torque on the disk about the point C. So to get that torque, we multiply the magnitude of T by the perpendicular distance of C to the line of action of T, which is R. So this is very similar to the problem involving a disk rolling down an incline. I'll mention that later. Okay, I is the moment of inertia about the point C. So for a uniform disk, we know that that's a half mr squared. Alpha is the angular acceleration. So alpha can be written as d omega dt, which is also d2 theta dt2. Now let's look at the forces acting on the disk. So the resultant force F is pointing downwards, of course, so I'll take that to be the positive direction. So the magnitude of the resultant force is mg minus t. By Newton's second law, that's equal to m times a. So we plug this in for t now. Well, we divide it by r first of all, and then plug in for t. Now let's look at alpha. Alpha is related to a because we have a case of a disk that's rolling without slipping, in a sense. It's the same kind of situation of a disk rolling along a surface without slipping. So the same reasoning that we saw in a previous video can be applied here. So as a reminder, I'll just go through that again. So we have a disk of radius r, and it rolls without slipping a distance x along the ground. So x is some function of time, of course. So the part of the disk that makes contact with the ground while it rolls from here to here, that part of the disk has length x of t. And we want a connection between x of t, the radius of the disk, and theta, the angle swept out. Well, if theta is in radians, we know that we multiply r by theta to get the sector, or the arc, created. The speed v of the center of mass of the disk is the derivative of this thing. So we've seen this before. R is just a constant, so we differentiate theta with respect to time. That gives us omega, which is actually varying in our situation. And if we differentiate again, we get the acceleration. d omega dt can also be written as alpha. Now alpha could be changing with time, but in all the problems we do, the forces are constant. So that means that alpha is constant. The angular acceleration is constant. Okay, so we just plug A over R in for alpha. So bringing this term over, we've 1 ma plus a half ma is 3 halves ma. So A is 2/3 g. Now we see that this answer makes sense. We would expect the acceleration of the disk to be less than the acceleration due to gravity. Okay, if the disk was just free to fall without any tension acting upwards, this would be the acceleration. Now, to get at this result, all you have to do is remember this result from a previous video. That's for a disk of mass m, radius r, rolling down an incline of angle theta. The acceleration doesn't depend on the mass and it doesn't depend on the radius. So what we imagine doing is make theta approach 90 degrees. So now we have the disk, well, in the limit as theta approaches 90 degrees. This is the picture. There's still a kind of a friction force acting. Well, that force is approaching zero, but we can actually use this formula if we let theta approach 90 degrees. If we take the limit, I'll just write it over here, limit as theta approaches 90 degrees of 2/3 g sine theta. The sine of 90 is 1, so this quantity 2/3 g sine theta will approach 2/3 g. That's the result that we got. Let's get the tension. So mg minus t is the mass times the acceleration. Well, we know what the acceleration is. So we get t equals 1/3 mg. So it's no surprise that the tension in the string depends on the weight of the disk. So the greater the weight, the greater the tension, because the disk is pressing on the string. By Newton's third law, the string pulls on the disk. Of course, the acceleration doesn't depend on the mass or the radius of the disk, so it doesn't matter how big or small this disk is or its mass, the acceleration is constant. If we go back to our problem of a disk rolling on an incline, we saw that the friction is given by this here, and you can see that as theta approaches 90 degrees, the friction force is approaching 1/3 mg. This is not the same as the limiting friction. The limiting friction is mu times the normal force. We explained in a previous video that for the wheel to roll without slipping down an incline, this value of F must be less than mu times the normal force. Okay. Anyway, we can see similarities. Now look at this situation here. We have a uniform disk that's rotating about an axle into the screen at its center of mass. So this axle is frictionless, perfectly frictionless. We have a mass attached to a light string that's wound around the disk. So the string's mass we can take to be 0. So let's look at the forces on this disk. Well, we can forget about its weight, which is vertically down, of course, because that's counterbalanced by a contact force on the disk due to the axle. Obviously, the force to consider is the force on this edge of the disk here. Well, it's a force on the string, if you like, but while this piece of string is in contact with the disk, this piece of string is part of the system of the disk. It has no mass, so the system is really consisting of the disk of mass, of certain mass, and of course this mass here. But we have a force on this bit of the string. Let's call that force T, and that force is constant, because as this mass falls down, its weight never changes. It's near the surface of the earth. The system looks the same, so this force T is constant as this wheel turns. So there's a torque on this wheel. torque about the center. As the only external torque is T multiplied by the radius of the disk. So let's say the radius is R. Okay, so I'm applying the principle of angular momentum, the sum of the external torques. Well, there's only one torque. Gravity has no torque on this disk. Well, you could say there's a torque due to gravity on this side of the disk. That's true. There is a torque about this point, but that's counterbalanced by an equal but opposite torque due to gravity on the other side of the center of mass. So the only external torque is due to the force T, and its magnitude is T times R. So just like we saw in the previous. So, you know, the principle of angular momentum tells us that that's the moment of inertia of the disk about the point C times the angular acceleration of the disk alpha. Now let's look at the forces on the mass M. We know that the string tension is the same throughout the string, and it acts away from points that the string is attached to. So let's take downwards as positive. Okay, so we have mg is acting downwards, minus T is the resultant force. By Newton's second law, that's mass times acceleration. Okay, we want to plug in for T, so the moment of inertia about C is a half mr squared for a uniform disk. So we get half mr alpha. Now, we want to connect alpha to A, the acceleration of this mass. But you see, this picture looks like a disk rolling. Okay, the string is leaving the disk. But that's, we could just imagine that this disk is rolling upwards. You know, and the string is like a surface. So it's rolling without slipping upwards, you know. As the string gets longer, it's like it's equivalent to the disk moving further. So it's the same kind of picture as a disk rolling along a surface without slipping. And what we are interested in is the rate at which the distance changes with time. Well, that's the speed of the disk, v, and the distance is x at t. So that's like the length of the string, if you like. So we know that x of t is r times theta of t. Okay, we've gone through this now several times. Here's theta, and this distance x is the same as the distance that the disk has moved along the ground, or the amount of string that has unraveled. So just like before, the acceleration is r times alpha, and that's constant. Alpha, we could put alpha of t, but actually alpha is going to be a constant because the forces acting t and mg are constants. So just like before, we have alpha equals a over r. So there we have it. T is a half ma. So interestingly, we get the same acceleration as we got for a disk that was falling down and unraveling. Now let's get the tension. Well, let's just go through this again. We have mg minus t equals m times a, where a is 2/3 g. Well, actually it's much easier just to plug into half ma, so half times m times 2/3, so the tension is 1/3 mg. Okay, so the tension is the same in this situation as it is for the previous example, the disk unwinding as it falls, and the acceleration of course is the same. The acceleration of this mass doesn't depend on this mass, or it doesn't depend on the mass of the wheel either, the mass or the size of the wheel. It's a constant. It's always 2/3 g. Now there are two ways that we could find the speed of this particle at any time. We could use the fact that we have the acceleration, which is constant, and we can use the formula v squared equals u squared plus 2as, where s is the distance travelled by the particle. So if we know the initial speed, we can find the final speed. For the acceleration, we plug in 2/3 g. Alternatively, we could consider the energy of the system. So here is the total energy of the system. Now I will show that this quantity is conserved. This is the rotational kinetic energy of the disk. Here's the potential energy of the particle, and here's the kinetic energy of the particle. So to use this formula to find V at any position or height h of the particle, we substitute for omega V over r. We know omega is V over r, or V equals omega r. Okay, for any rolling or turning disk, that's a piece of string on the edge of the disk. Its speed is related to its angular speed omega through this relation. Again, this result comes from what we saw earlier with a rolling wheel. X is r times theta, so if we differentiate, okay, so the distance x that a piece of string travels is r times the angle, theta in radians. So if we differentiate x equals r theta, we get V equals omega r. Okay, so for the uniform disk, I is a half m r squared. That's I about the center of the disk, of course. That's the rotation point. So we've 3/2 m times 1/2. So we get down to this here that we could use as a formula. So if we know the speed and height at one instant, and we can solve to find the speed or height at another instant. So this quantity is a constant, which I'll show at the end of the video, but if we know the speed at one instant, say at one instant the speed is v1 and the corresponding height is h1, then because this thing doesn't change, at another instant when the speed is v2 and the height is h2, this quantity has the same value as this quantity. They're both equal to the same constant, which would be the total energy at the start of the motion, if you like, or at the end of the motion. Okay, if something's equal to a constant, then its value at one instant is equal to its value at another instant, where both are equal to this fixed value. So we've 4 unknowns, but if we know any 3 of them, suppose we know v1 and h1 at a particular instant, and we know we want the speed at a new instant when the height of the mass above a reference level is h2, well, we can just go and solve for v2. So we will just prove it for the uniform disk case. So we plug in for I half mr squared, and it boils down to this, as we've just seen. So we'll just prove that this quantity is conserved. Okay, so we use the acceleration that we got from the previous part, and the fact that v squared is u squared, the initial speed of the particle, plus 2as, where a is 2/3 g. So 2 times 2/3 is 4/3 g, and s is the distance travelled. Okay, so that's just the formula, u squared plus 2as. Now we want to relate the height of the particle above some reference level to the distance travelled s by the particle. So let's suppose that the initial height of the particle was big H, so the particle started here and it travels a distance s to get to here. Okay, so initially it was here with speed u, and eventually it gets to here after travelling a distance s, and it has speed v. Alright, so big H is obviously fixed, so it's s and little h that vary. So you can see that little h is just big H minus s. So the key thing here is that the terms that involve s need to disappear, because s is the only variable now. Big H is fixed, u is fixed, and indeed they do. So what we end up getting is this constant 3/4 mu squared plus mg big H. U is the initial speed, h is the initial height, but this is just the initial energy of the system. You can see that it's the same as this here, just replace v with u and little h with big H.